Okay guys, now we look at using derivatives to find turning points and finding the nature of the turning points. So I'm going to teach you two ways here. So first, find the stationary points of this graph and state their nature. So we find f dash of x, which is going to be 9x squared minus 4. We know f dash of x equals 0 for a stationary point. Okay, so if we let 9x squared minus 4 equals 0, we get 9x squared equals 4. We get x squared equals 4 on 9, and x equals plus or minus 2 on 3. So find the stationary points and state their nature. So if x equals 2 on 3, we need to find y. And if x equals negative 2 on 3, we need to find y. A little bit painful. So f of 2 on 3, if I put that into the equation, I get 3 times 8 on 27 minus 4 times 2 on 3 plus 1. That's going to give me a 9 on the bottom. So I get 8 on 9 minus 8 on 3 plus 1. Let's put it all over a common denominator of 9. So that's 9. That's going to be 24. That's going to be 9 over 9. So I've got 8 plus 9, which is 17, minus 24. I get negative 7 on 9. So that's our first point. 2, negative 7 on 9. F of negative 2 on 3. When I cube it, I get 3, negative 8 on 27, minus 4 times negative 2 on 3, and then plus 1. So I get, that will cancel with that, give me a 9, negative 8 on 9, plus 8 on 3, plus 1, same denominator, 9, 24, 9 on 9. So I've got negative 8 and then plus 33. So that's going to be 25 on 9. So they're my turning points. Now, it says to find their nature. So what you can do, I'm going to just rub these out because I need some space. Now we know what the turning points are. So I can create what's called a gradient table. So 1, 2, 3, 4, 5. So we know at the point negative 2 on 3 and at 2 on 3, they've got 0 gradients. We can choose something to the left of negative 2 on 3. So when x equals negative 1, because that's the left of negative 2 on 3. If I put that into the derivative, I get f dash of negative 1, which is 9 times negative 1 squared minus 4, which is 9, take away 4, which is 5. So we know it's got a positive gradient because dy dx is positive. So it's got to be going up. Something in between negative 2/3 and 2/3 is 0. So if I put 0 into that, f dash of 0 is equal to 0 minus 4, which is negative 4. So we know here it's got a negative gradient. So we know this point here, if we look at its shape, that is a maximum, because it's going up to a maximum point and then coming back down. Now if we find f dash of 1, a point to the right of this, we can see, if I put a 1 into that, I get 9 minus 4 again, which is 5, so it's got a positive gradient. So this point here is a minimum. So we know this point here is a minimum, because it corresponds to 2/3, and this point here is a maximum, because it's curving downwards. Now, there is a much easier way, and that's using specialist maths, but it's quite okay to use it in methods as well. So we know that f dash of x is 9x squared minus 4. F double dash is when I derive this again. So it's like if you got your displacement, you're finding your acceleration. So if we derive it again, we get 18x. Now the way we test and see whether it's a maximum or a minimum, if f double dash of x is less than 0 i.e. negative, it's a max. If f double dash of x equals 0, then it's a point of inflection. If f double dash of x is greater than 0, then it's a minimum. So we can test using the values that we did before. So f double dash of 2/3, 18 times 2/3, well, that's going to give me a positive number, and a positive number is a minimum. And that's what we said before. We said that this point was a minimum, and then at this point here is a maximum. So let's test that. If I put f double dash of negative 2 on 3, I get 18 times negative 2 on 3, which is negative, and if it's negative, it's a maximum. So we know this point here is a maximum. So you can do it with the gradient table, or you can do it with the second derivative. You've got to sub the x value into the second derivative. If it's negative, it's a max. If it's positive, it's a min. If it equals 0, it's a point of inflection, which I'm not sure. I'm sure we've gone through that actually. Okay, so here we're looking to find our stationary points in this graph. So I've got to sketch the whole graph. So when we sketch a graph, let's first get our x and y intercepts. So if we let x equal 0, we get y equals 0. If we let y equal 0, we get 3x squared minus x cubed equals 0. We know we can take out x squared, so we get 3 minus x. So we get x equals 0 or 3. Now we know, because that's a repeated factor, that's also a turning point. But let's use our derivatives to prove everything. So dy dx is 6x minus 3x squared. We know dy dx equals 0 for a stationary point. So if we set 6x minus 3x squared equal to 0, we can take out 3x as a common factor, and we get 2 minus x equals 0. From this, we get x equals 0 or 2. So we know we have got x-intercepts, 1, 2, 3. We've got x-intercepts at 0 and 3. And we've got stationary points at 0 and 2. When x equals 0, y equals 0, so we already knew that point. When x equals 2, y equals 3 times 4 minus 8, which is 4. So we know we've got the point 2, 4. So 1, 2, 3, 4. 2, 4 is there. 2, 4. We know 0, 0 is a turning point. We know it's a negative x cubed, so it's got to go down. So it's got to go down like that. So there's 3, 0. That's a turning point, so it's got to go down. And we know the point 0 is a turning point, so it's got to curve something like that. Although that's a terrible graph. So let's say it goes like that. Okay, because we knew this was a repeated factor, now we can prove that this is a max and that's a min. First, let's find our second derivative. So our second derivative, just like with f double dash of x, the second derivative with dy dx is d squared y dx squared, because we're deriving it with respect to x twice. So we say d squared y dx squared. My second derivative is the derivative of that, so it's going to be 6 minus 6x. If we find d squared y dx squared when x equals 0, we get 6 minus 6 times 0, which is 6. Because it's positive, it's a min, and look, it's a min. Then we find d squared y dx squared, given x equals 2. We get 6 minus 6 times 2, which is negative 6. Now, if the second derivative at a point is negative, then it's a maximum. So we've said this point here is a maximum, which it is. So we found the graph showing the stationary points and the x-intercepts and the y-intercepts. Okay, this one here, it's nice and factorized for us already. So when x equals 0, y equals 0, because if I put 0 into that, I get 0. When y equals 0, 0 equals x cubed, 4 minus x squared, no, 4 minus x. So x equals 0 or 4. Now, because this is repeated 3 times, it's not a turning point, it's a stationary point of inflection. But we'll show that because the second derivative should equal 0 at that point. Okay, so first, let's expand it out. Y equals 4x cubed minus x to the 4. dy dx is equal to 12x squared minus 4x cubed. dy dx equals 0 for a stationary point. Okay, so then if I say 12x squared minus 4x cubed equals 0, we can take out 4x squared as a common factor. We get 3 minus x equals 0. So x equals 0 and x equals 3 are my stationary points. When x equals 0, y equals 0, because we know from this graph, if I put 0 into it, I get 0. If x equals 3, I'm going to get 27 times 4 minus 3, which is 1, so it's just 327. Okay, so at the moment, we have got an x-intercept of 4 and 0, 0. It's a negative x to the 4, so it's going to be going down at the end. Okay, we know that this is a point of inflection, and that's an x-intercept. We also know it goes through 3 and 27. I don't know what I just clicked. Okay, so when we go across to 3, it's got to go through, let's say that's 27. So there's 327. Okay, now let's see what the nature of these points is, whether they're maximums, minimums, or points of inflection. So we just got to prove it. So this is dy dx. So d squared y dx squared is 24x minus 12x squared. D squared y dx squared, when x equals 0, is 24 times 0 minus 12 times 0, which is 0. So if the second derivative equals 0, then it's a stationary point of inflection. D squared y dx squared, when x equals 3, is 24 times 3 minus 12 times 3 squared. 24 times 3 is 72. 12 nines are 108. So it's negative 36. So that point is a maximum. So we know here's a maximum, so it's got a curve like that. So it's got to go down. And we know this is a point of inflection, so it's got to come down, flatten out. I'm just going to move this out of the way. 0, 0. It's got to flatten out and then come back down again. So that's what this graph looks like. That's the shape. And we know that point there is 327. Remember, a point of inflection is when I've got a positive gradient, 0 gradient, and then a positive gradient again. Or if you had a negative gradient, a 0 gradient, and then a negative gradient again. That's a bit exaggerated there. Okay, this is a bit of a long chapter. Okay, so sketch the graph of e to the x cubed. So f dash of x, we know, is the derivative of the power, 3x squared, times e to the x cubed. If we let x equal 0, we get y equals 0. If we let y equals 0, we get, if we let x equals, I've got to start this one again. Sorry, I did the derivative before I should have. So if we let x equals 0, f of 0 is e to the 0, which is 1. So we know it goes through the point 0, 1. If let y equals 0, we get e to the x cubed equals 0. Now we know e to the x is greater than 0 for all x. So there is no solution, because it's always going to be greater than 0. Now let's have a look at the derivative. F dash of x is 3x squared e to the x cubed. If we say f dash of x equals 0 for stationary point, so we get 3x squared e to the x squared cubed equals 0. So we either get 3x squared equals 0 or e to the x cubed equals 0. Now we know this has no solution because e to the x is greater than 0 for all x, whereas here x equals 0 is a stationary point. Okay, so we can see what type of stationary point it is. Probably the easiest thing with this one is to draw a gradient table. So we've got 0. E to the x we know is greater. It's never going to be bigger than less than 0 or equal to 0. It can't equal 0 because it's e to the x. So y equals 0. We know it goes through 1, and that's also a stationary point. Okay, so when it's 0, it's got a flat gradient. When it's 1, if we put 1 into the derivative, we're going to get 3 times 1, which is 3, or 1 squared, and then times e to the 1. So we're going to get 3e, which is positive. So it's got a sloping upwards gradient because we chose a point to the right, 1, and it's got a positive gradient, so it's going to keep going up. Okay, let's try -1. If we put -1 into it, we get f dash of 1 is 3 times -1 squared times e to the -1 cubed, which is 3 times 1 times e to the -1, which is 3 times 1 over e, which is 3 over e, and that's still positive. So it's got a positive gradient on this side. So it basically just looks like a normal exponential graph. But what did we forget? We forgot that it's got to flatten out. So it's got to go up, flatten out to 0, and then it's got to climb up again, because it's got 0 gradient there. So that is actually a point of inflection, and we can test it. If we find f double dash of x, we're going to need to use the product rule. So we derive 3x squared and we get 6x, and then we multiply that by e to the x cubed, plus we derive e to the x cubed, which is 3x squared e to the x cubed, and then we multiply it by 3x squared, which is 6x e to the x cubed, plus 9x to the power of 4 e to the x cubed. F double dash of 0, if I put 0 into this, 6 times 0 is 0, 9 times 0 is 0, so our second derivative equals 0. So that means that it is it's a point of inflection. because our second derivative equals 0, it goes up. It'll flatten out at that point. This is an exaggeration, by the way. Flattens out, and then it goes back up again. And let's have a look. If we sketch it, we should be able to see that. So e to the x cubed, graph of e to the x cubed. Let's initialize. So you can see it climbs up, it flattens out, and then it continues to go up, which is exactly what we just did. So it is pretty exaggerated. Okay, let's try and get through these ones quickly. So I've got x log ex, find f dash of x, so I've got to use the product rule. So f dash of x, derive that, I get 1, leave that alone, 1 log ex. Derive log ex, I get 1 on x, and then leave x alone, I get times x. So it's log e x plus 1. Solve f of x equals 0. So x log e x equals 0. So I get x equals 0 and log e x equals 0. Here, I get x equals e to the 0, which is 1. So it's got x-intercepts at 0. But we can't log 0, can we? So that one, x equals 0, but it's not a solution because it's out of domain. Because if you have a look up here, 0 is not included and we can't log 0. So we know we've got a point that's not included there, and we know that when x equals 1, we've got an x-intercept. Okay, solve f dash equals 0, so log e of x plus 1 equals 0, x log e of x equals negative 1, x equals e to the negative 1, x equals 1 on e. When x equals 1 on e, f of 1 on e is equal to 1 on e times log e of 1 on e, which is 1 on e times log e of e to the negative 1. So I get negative 1 on e, because I can bring that negative 1 down to the front. Log e of e is just 1, so I just get, my point is 1 on e, comma, negative 1 on e. Now 1 on e is about 1 on 3, this is approximately, and then negative 1 on 3. So let's go 1 on 3, negative 1/3, so let's say it's there. So that's 1 on e, negative 1 on e. So our graph's going to go down, and then I think it's going to go up. But we can test it. So let's find our next derivative. So we know f dash of x is equal to log e x plus 1. So f double dash of x, log ex, when I derive it, I get 1 on x. 1, when I derive it, I just get 1. So my second derivative is 1 on x. When x equals 1, we know f double dash of 1 is 1 on 1, which is 1, which is positive. So we know it's a minimum. So this comes down to that point, and then it continues up. Because there's no more turning points, it's got to increase, like it's got to keep going upwards. Okay, so it'll look like that, and it's undefined at that point, so that should be an open circle. So that's x log ex, so let's have a look and make sure we got it right. Okay, so x times natural logarithm of x, just the 1's fine, and we get that graph, and you'll see If I try and trace it, if we put in 0, it's undefined because you can't log 0. Okay, find the local maximum minimum values of that. Okay, so we've got fx equals 2 sine x plus 1 minus 2 sine squared x. So if we find the derivative of this, we've got to rewrite it first, because in our cas, that there, sine squared x is the same as sine of x all squared. So f dash of x is, when I derive sine, I get cos, so I'll get 2 cos x. When we derive 1, we get nothing. When we derive, we've got negative 2. When we derive sine x all squared, we bring our 2 down to the front. We multiply it by the derivative of the bracket, so the derivative of sine x is cos x. Then we multiply it by the bracket, sine x. So we get 2 cos x minus 4 cos x sine x. Now it says find the maximum and minimum values. So if f dash of x equals 0, we get 2 cos x minus 4 cos x sine x equals 0. We can take out 2 cos x as a common factor, and we're left with 1 minus 2 sine x equals 0. So we get 2 cos x equals 0, and then we get 1 minus 2 sine x equals 0. Here we get cos x equals 0. So when does cos x equal 0 between 0 and 2 pi? It equals 0 at pi on 2 and at 3 pi on 2. If you're unsure, just draw a quick graph. There's cos. That equals 0 at pi on 2 and 3 pi on 2. Then we get sine x equals 1/2. So 1, 2, root 3. So my angle's got to be pi on 3. So x equals pi on 3. And then where else is sine positive? Sine's positive in the first and second quadrant, so it's going to be 2 pi on 3. Okay, so we've got pi on 2, 3 pi on 2, pi on 3, and 2 pi on 3. Now to find out whether they're minimums or maximums, we have to find the easiest thing to do is to find the y values, because then you'll be able to tell whether it's a maximum or a minimum. Okay, so if I put pi on 2 into the top one, f of pi on 2, we know that sine of pi on 2 is 1, so I get 2 times 1 plus 1 minus 2. Sine of pi on 2 is 1, 1 squared is 1, so minus 2. So I'm going to get 2 plus 1 minus 2, that's going to be 1. If I put 3 pi on 2, we know that sine of 3 pi on 2 is negative 1, so I get 2 times negative 1 plus 1 minus 2, and then times sine of 3 pi on 2, which is negative 1, squared, which is 1. So I've got negative 2 plus 1 minus 2, so that's negative 3. If I put pi on 3 into it, I get 2 sine of pi on 3, which 1, 2, root 3. That's root 3 on 2, plus 1, and then minus 2 times root 3 on 2 squared. So we're going to get, that's root 3 on 2. So I get root 3 plus 1 minus 2 times 3 on 4, which is 3 on 4, that's 3 on 2. So I get 1 plus root 3 minus 1.5. So that's going to be root 3 minus 1/2. And then if I get 2 pi on 3, we're going to get exactly the same value. because sine is positive in both of them. So we're going to get root 3 plus 1 minus 3 on 2. So that's going to be root 3 minus 1 on 2. So this question's a little bit annoying because we've got to work out whether these are maximums or minimums. You can find the second derivative. Okay, 1, negative 3, root 3 minus a half, root 3 minus a half. Let's have a look. 2 sine x plus 1 minus 2 sine squared x. 2 sine x plus 1 minus 2 sine x, and then all squared. Okay, and we want it between 0 and 2 pi. So let's just go 0 to 2 pi. So there's our graph. So we've got a maximum at, that must be pi on 3. No, that's not pi on 3. What is that? We've got a maximum at pi on 2. Then another maximum at, that must be 2 pi on 3. So that's a max. That's a max. That's a min, but we mustn't get the same value. I must have stuffed something up. I can't be bothered trying to work it out. Where are we? So if we go analysis G solve min, we'll see that there's a min at pi on 2. Oh, so one max is there, which is pi on 3. That's one max. Then another max. So your max is at pi on 3 and 2 pi on 3. And then your mins are at pi on 2, 1, and at whatever that value is. So these are both maxes. Max, max, and then min, min. You could also use a gradient table. That's going to be a pain in the butt there. Okay, lastly here, I've got a graph. To sketch it using a CAS, you just put that in. So x cubed minus 9nx plus 20. X cubed minus 19x plus 20. Sketch it. Zoom, initialize. Okay, you've got your 3x intercepts. So you know one occurs at negative 5 and the outside one occurs at 4. So go negative 5 and then go up to 4. Click OK. Then go zoom auto. So it fits in the graph perfectly. Analysis G solve root will tell you what your x-intercepts are. 1, 2, 3. So I just did that. If you want your exact intercepts, you can just grab this, copy, go out to main, clear whatever's there, paste it, set it equal to 0, interactive advanced solve, make sure it's in standard. They're pretty nasty. Simplify I don't think is going to do much. Okay, so we'd get them as decimals. Okay, but the easiest thing to do is go into your graph. If you want to find that maximum, analysis G solve max, and it'll tell you the maximum. If you want to find analysis G solve min, and that is, zoom out. So analysis G solve min, that tells you a minimum. Analysis G solve max, that tells you a maximum. Analysis G solve root tells you your x-intercepts. Analysis G solve y-intercept tells you your y-intercept. I don't really think there's going to be anything else. You can actually find your maximums and minimums. like the exact values. So with this function, we know that our maximum occurs between -3 and -2. So we can grab the function. Where did it go? We can grab the function, go out to here. Oh, because that was when I was trying to find intercepts. Okay, edit, paste, interactive calculation, max, fmax, and we know it was between -3, -2, and it tells us that's our maximum value, and it occurs when x equals that. And then our minimum, oops, that occurred at about between 2 and 3. So we can go and do the same thing. So grab the function, interactive calculation min, and that occurred between 2 and 3, and that tells us what our minimum is. You could also derive it and set it equal to 0, so that d dx equals 0, and solve, interactive advanced solve. And then I've got my x-intercept. So when I find out what y is, I just do that function, and then given x equals, that's my y value. And then I do the same thing again. That's my y value when x equals that. So they're my turning points. So that is everything for that chapter. So you can use your calc, all the information's in the notes, but we've just gone through most of it on the CAS.